Welcome back, everyone! For years, carbon nanotubes have promised to outperform silicon in speed, efficiency, and miniaturization, but the technology has struggled to make the leap from laboratory to production. That is now changing. Several semiconductor companies have quietly advanced the manufacturing processes required to build processors using carbon nanotube transistors. These tiny cylindrical structures, just a few nanometers wide, offer extraordinary electrical conductivity and the potential to pack more transistors into a chip without overheating. With recent announcements and prototypes, it is becoming clear that carbon nanotube processors are no longer experimental. They are ready for real-world markets. Carbon nanotubes are cylindrical molecules made entirely of carbon atoms arranged in a hexagonal lattice. These tubes are only a few nanometers in diameter, but can be several micrometers long. Because of their size and structure, they exhibit exceptional electrical conductivity and thermal properties. When used in processors, carbon nanotube transistors allow electrons to move with much less resistance than in traditional silicon. This means signals can travel faster with less energy loss. The goal of researchers has been to arrange these tubes precisely on a chip to create functioning circuits, which is now becoming technically feasible at scale. To make a processor out of carbon nanotubes, engineers must grow or deposit the nanotubes onto a substrate in a highly ordered pattern. This involves using chemical vapor deposition and advanced placement techniques that guide the tubes into the desired alignment. Once placed, the nanotubes are connected with metal contacts and insulating layers to form transistors and logic gates. These circuits function similarly to silicon-based processors, but can operate faster and at lower voltages. Manufacturing at this level of precision has required breakthroughs in material science and process engineering to eliminate defects and ensure consistency across billions of transistors. A key feature of carbon nanotube transistors is their ability to switch on and off more rapidly than silicon equivalents. This is due to their high carrier mobility, meaning electrons or holes can travel through them more freely. Additionally, carbon nanotubes generate far less heat during operation. This reduces the need for elaborate cooling systems and opens the door for smaller, more efficient processors. Because heat is a major limitation in silicon chip design, this advantage allows more transistors to be packed into a smaller area without the risk of thermal failure or performance degradation under load. Carbon nanotube processors can also be fabricated on flexible substrates, unlike rigid silicon wafers. This creates opportunities for new device formats, including bendable electronics and ultra-thin embedded processors. The ability to manufacture advanced computing elements on plastic or polymer sheets could revolutionize wearable technology, implantable medical devices, and smart textiles. This flexibility is due to the mechanical properties of carbon nanotubes, which are incredibly strong yet lightweight and adaptable. As production methods improve, manufacturers will be able to integrate carbon nanotube processors into places where traditional chips simply cannot be used. Another crucial benefit of carbon nanotube transistors is energy efficiency. These devices require less power to operate, which directly translates to longer battery life for portable devices and reduced electricity use in data centers. As global demand for computational power increases, energy efficiency becomes more important. By replacing or supplementing silicon components with carbon nanotube equivalents, companies can build faster processors that consume less power. This is especially relevant for artificial intelligence workloads, which require rapid and efficient data handling. Reduced power usage also helps lower the environmental impact of large-scale computing infrastructure. One of the greatest challenges in building carbon nanotube processors has been controlling the purity and uniformity of the nanotubes themselves. Early efforts often resulted in mixtures of metallic and semiconducting tubes, which interfered with performance. Recent developments in sorting and purification techniques now allow manufacturers to isolate only the semiconducting nanotubes needed for transistors. Additionally, researchers have developed ways to remove misaligned tubes and other contaminants during the production process. These improvements are essential for achieving the levels of reliability and consistency required for commercial processors used in high-performance computing applications. Compatibility with existing manufacturing infrastructure has also been addressed. Some of the latest carbon nanotube chips can actually be produced using modified versions of current semiconductor fabrication tools. This reduces the cost and risk of transitioning to the new technology. Foundries that already make silicon chips can, with just some adjustments, begin integrating carbon nanotube layers or even entire carbon nanotube architectures. This kind of hybrid approach allows the industry to test carbon nanotube performance in real-world conditions while still maintaining compatibility with traditional chip designs. It also helps accelerate adoption by minimizing the need for entirely new manufacturing plants. Carbon nanotube processors also enable new methods for signal routing and interconnects on the chip. In traditional silicon processors, metal traces connect transistors, but these connections can become bottlenecks as transistor density increases. Carbon nanotubes, thanks to their exceptional electrical conductivity, can serve not only as active transistors, but also as interconnects between components. This dual function reduces complexity and improves signal integrity. Engineers are experimenting with vertical and multi-layer architectures where carbon nanotubes serve as both logic and wiring, enabling more compact and faster chips. This structural versatility is one of the reasons carbon nanotube processors are now seen as a viable successor to silicon. The testing and verification process for carbon nanotube processors includes benchmarking their speed, power consumption, and durability under various workloads. So far, prototype devices have demonstrated performance comparable to or better than their silicon counterparts. Researchers continue to refine the architecture to maximize the advantages offered by carbon nanotubes. This includes exploring new logic designs that better exploit the properties of the material, as well as integrating machine learning algorithms that can take advantage of faster data access. Over time, these optimizations will lead to processors that are not only faster, but also more intelligent in how they manage tasks. Carbon nanotube processors are expected to enable a new generation of wearable and implantable computing systems. Because they consume less power and can be fabricated on flexible substrates, they open the door to electronic devices that are not limited by rigid form factors. This could lead to medical implants capable of real-time health monitoring or diagnostics without frequent battery changes or bulky housings. In consumer products, smart clothing with embedded computation and seamless communication could become commonplace. Devices that currently require regular charging or wired connections may become persistent, ambient, and nearly invisible components of everyday life thanks to the low power operation and mechanical adaptability of these processors. Another major frontier lies in space technology and high reliability applications, where radiation resistance and thermal stability are critical. Carbon nanotube processors are inherently more tolerant to cosmic rays and temperature fluctuations than traditional silicon-based chips. This makes them ideal for long-duration satellite missions, planetary rovers, and even deep space probes where maintenance is impossible. In extreme environments on Earth, such as polar stations, underwater exploration vehicles, or high-altitude platforms, these chips could outperform conventional electronics while remaining lightweight and energy efficient. As fabrication techniques mature, entire computing systems optimized for durability, resilience, and flexibility will emerge, enabling machines to operate where current systems would fail. As carbon nanotube processors enter commercial production, they could reshape what we expect from consumer devices, scientific computing, and artificial intelligence. Their ability to operate faster and cooler than traditional silicon could accelerate progress across the tech sector. Investors are watching closely, and early adopters are already positioning themselves for access to this leap in processing power. While large-scale adoption will take time, the industry has reached a critical milestone. Carbon nanotube processors are no longer just a research ambition. They are arriving in real products, and their presence could signal the next major shift in the evolution of computing. Thank you very much for watching. Please comment, like, and subscribe.